All right, let's take a look at the last pod. This was something that threw me for a while when I was in graduate school. I tried to buy a bottle of cyclopentadiene, and you cannot buy a bottle of cyclopentadiene, and I couldn't figure out why. And then my advisor rolled up a newspaper and hit me with it. And he said, "Dummy, you can have a retro Diels Alder reaction." So this is what inspired this problem of the day, was a rolled up newspaper. If you think about cyclopentadiene, it can act as both a diene and a dienophile. So over here I'm going to treat one of these as a diene, and I'm going to treat another one as a dienophile. And when you react these, you can do it in a similar way to what we saw yesterday, where one of these pi bonds will hop down, the other one will hop over, and this one will hop over. Now when you do this, you'll end up with a new ring system where you've got a double bond here, and then you'll also run into this diene over here where you've got this double bond coming off of this position. So I'm trying to show that diene in a relative position so that it's going underneath. Another way of looking at this is using that Sideon view. So I'm going to show you the product using the Sideon view. Oop. Where we've got these two hydrogens sticking out over here, and we've got our double bond down here. Is this our endo or our exo product? Endo. So if you notice, that second equivalent of cyclopentadiene, the one that was acting as our dienophile, is actually located underneath. So it's on the opposite side of the ring as this roof. So if we look at this roof position right here is sticking closest to our eye. However, the dienophile is actually going to be located underneath, so we need to draw that using the correct stereochemistry. Endo product is almost always favored in these sorts of situations. However, you may occasionally see in other organic textbooks the endo product being favored. We're not going to get into much more than just saying that the endo product is usually the observed product in this case. All right, now part 2 is looking at this reaction, and it's saying, well, how can we get this reaction to go in the reverse direction? And so let's take a look at a simple Diels Alder reaction. And I've got my diene and I've got my dienophile, and I'm going to form a simple Diels Alder product. If we think about this, we are going to break 3 pi bonds, and we are going to make 1 pi bond, and we are going to make 2 sigma bonds. Do you guys think that the delta H for this reaction will be positive or negative? Well, let's think about this. For this forward reaction, for a normal Diels Alder reaction, the net is going to be that we break 2 sigma bonds, and we're going to make 2 sigma bonds. Right? So let's think about this in terms of breaking it apart. Does it take energy to break bonds, or does it create energy? It takes energy to break a bond, right? So the delta H value for breaking bonds will be positive. Right? Making bonds releases energy, so that delta H value will be negative. What's stronger, a sigma or a pi bond? Sigma bond. So a sigma bond is a point-on interaction, so you have more orbital overlap than adjacent pi bonds that are parallel to one another. So in this case, do you think the delta H is going to be more positive or more negative? More negative, because that value for the sigma side is going to be much, much greater. So delta H for this reaction is negative. What about delta S? Well, let's think about it. Things become more positive in terms of entropy when we create more disorder. Are we creating more disorder? No. So in this case, delta S is going to be negative. All right, so now let's break this down into our Gibbs free energy equation, right? We know delta G equals delta H plus negative T delta S. So if we look at the Diels-Alder reaction, we know that delta H is going to be negative. What about this negative T delta S term? Yeah, the two negatives will cancel out. This will become positive. So if we think about this, we've got a negative plus a positive. That means that temperature plays a really big role. So if temperature is low, delta G is going to be positive or negative? Yeah, delta G is negative. And the reaction favors the Diels-Alder product, right? So it favors the product side of the equation. However, if we think about the temp being high, things change. Delta G, if temp is high, now actually becomes positive. It overcomes that enthalpy value that is negative, and delta G is positive. And now the reaction favors the starting materials. So with the Diels-Alder reaction, you're running into the same situation that we saw in first term, where it's very dependent on temperature. In fact, oftentimes we have to add catalysts to a Diels-Alder reaction, because if we run the reaction too hot, it actually hinders the reaction. Because entropically, a Diels-Alder reaction is disfavored. We're taking 2 moles, turning it into 1 mole. So you don't want to apply too much heat. In fact, if you apply too much heat, you'll split it apart back into your starting materials. So it's getting back to first term stuff. You guys thought you got away from entropy and enthalpy, didn't you? Yep.
Wasn't the prompt to do retro? Yeah.
What's that?
Wasn't the prompt to do retro?
Yeah, but in this case, what I'm saying is, if we're looking at this case, we're trying to favor the starting materials, right? So in this case, we want to raise temperature so that we go back to our starting materials from our Diels-Alder reaction in the first step.
So could we have done this like completely backwards?
Yeah, I have to take a look at what you guys wrote. I just wanted you guys to think about entropy and enthalpy a little bit. And there's a section in your book that discusses this in a little bit more detail if you're interested in reading about it some more. All right, so let's go back to where we finished off yesterday. So yesterday we talked about endo versus exo addition, and I gave you guys this example. And I said that exo addition is where you kind of have the side-on docking. It's not an overlapping sandwich. And endo addition is where you've got this overlapping sandwich of your diene and your dienophile. And the endo addition is normally favored due to this electronic stabilization that occurs. And you can draw this using a few different views. You can do the top-down view, you can do the side view, but make sure that you clearly show stereochemistry for these. All right, now I've got another warm-up problem for us. Oops, sorry. This is in the wrong spot. We've got these reagents, and we want to figure out what the product is, and we need to show it with the correct stereochemistry. So it may help to draw this using a side-on view or a boat view or something like that, where you can clearly see the endo orientation. I'm going to do the Sideon view a little bit to help you guys get started if you're stuck. So I'm going to label these as CH3s. And then underneath, we're going to have our dienophile. And should this nitriles be pointed underneath the ring or away from the ring? Underneath, right? The Endo rule says that these cyano groups prefer to be located underneath the ring. And then if we think about the bonds being made and broken, we're going to have this docking that occurs underneath here. We're going to break this pi bond. We're going to break this pi bond. We're going to break this pi bond. And we're going to make this pi bond. So this is our transition state. And this is going to be our Sideon view. And now we have to consider our product from the Sideon transition state. I'm going to draw two different ones. So we've got these nitriles here and here. All right, so if we look at these, let me zoom out a little bit. These are our two potential products. Which one's more likely, the one on the left or the right? And then I'll fill in the methyl groups in a second here. Will the nitrile groups be pointed down or out and away? Down. So if we look at this one on the right, this one on the right is not likely. But now we've also got to consider the methyl groups coming off, right? Because we had these methyl groups here and here. And we have to show them coming off of the ring. So if we think about the protons, I'll highlight the protons using a blue color here. Or sorry, not blue, pink. These ones will actually be sticking up, kind of like that roof we saw with the cyclopentadiene. And then our methyl groups will be sticking out and away, kind of. Does that make sense? Mm-hmm. So if we look at this one, we could say this one, our theoretical product would be our exo product. However, we know that our endo product is more favored. So let me just circle this and say exo is not favored. And this Sideon view is a little bit tricky, right? So what I want you guys to do is to figure out a better way to draw this using a two-dimensional view using a normal hexane ring. So let's draw this molecule on the left using a normal cyclohexene ring, two-dimensional top-down view. So imagine your eyeball looking down directly on this. Yep.
So in the transition state, why did we put the hydrogens going up for the top part? Couldn't we just switch the methyl and hydrogen?
Well, think about the methyl groups coming off. They have to be pointed out.
Oh,
because if we look here, these methyl groups are pointed out. However, in the final product, these methyl groups kind of end up pointing up. But these methyl groups are still sticking out and away.
So is it because of that first drawing?
Yes.
If those were pointed in, then...
Exactly. The orientation of the alkenes is trans, which means that the methyl groups have to be pointing out from our new ring system. How many of you guys think you got the cyclohexane drawing? Okay, a few of you. Let's get this started. We've got our double bond on the left. Our hydrogens are going to be wedges because they're closest to our eyes, so I'll just draw these both as hydrogens. Our methyl groups will be dashes. And then if we go over here, these protons, are they going to be closer to our eye? Should they be wedges, or are they further away? Should they be dashes? Closer. So we want to draw these as wedges. Cn and Cn. So if we look at this, this would be our major Diels Alder product for this reaction.
Can we just draw the dashes for methyl and Cn?
Yeah, you don't have to show hydrogens if you show stereochemistry for the other substituent. Yeah. Yep.
So why are we having the methyls as one pointing back and not the one, not like the main parts of the ring that are pointing downward as the dashes instead?
Can you say that again?
So with the ring, we have part of the ring pointing down away from us, and the methyls are kind of sticking straight out. So why don't we draw the methyls as like a straight?
Oh, are you saying why don't we draw these bonds as dashes?
Yeah.
You can. However, oftentimes people prefer to draw it this way just because it's a little bit clearer. Oftentimes with a ring system, you don't draw a portion of your ring as a dash or a wedge. You want to draw the substituents using dashes and wedges. That's just generally how it's shown. Yeah. It wouldn't be wrong, yeah. As long as I can clearly see your stereochemistry and you clearly understand your stereochemistry, that's all I really care about. You can draw it from a top-down view, you can draw it with a boat view, you can do a side-down view. I really don't care, as long as you understand the stereochemistry. Yep.
Why is the exo not favored and we choose the endo?
Because, as we saw up here, with the endo addition, when you've got these electron withdrawing groups, so in this case we've got all these oxygens, they prefer to be underneath your diene during the Diels-Alder docking. They don't want to be sticking out and away. So if we look at this one, we've got cyano groups. They're really electron withdrawing. They want to be underneath that pi system during that docking step.
If they were methyls, would they still be underneath or?
Yeah, if they were methyl groups, in that case they're not electron withdrawing. You might actually observe more of your exo product. But in this case, we're primarily concerned with our electron withdrawing groups being underneath the ring. All right. Do you guys want to do another endo versus exo one or continue on? One more? All right, one more. I've got a good one. Brace yourselves. Come on. There we go. All right, this is a very famous Diels-Alder reaction. Let me shoot. My pen is not happy today. Just 1 second. Come on. All right. So we've got OTMS. Does anybody remember what TMS stands for? Yeah, trimethylsilyl. Let me draw it bigger. This is a very famous diene. This is called Danishevsky's diene. I'll spell it.
I don't use IC. I use CAM.
Well, if I made a diene, I'd call it an Engel diene. I wouldn't call it by its IUPAC name. All right. It's selfish. All right, and we've got this as our dienophile. Let's draw our product from this reaction. I'm going to do the Sideon view. You can draw it a different way if you'd like, but I really prefer the Sideon view. So that's our overall skeleton for our Sideon view. Should the dienophile be pointed down into this direction, or should it be pointed out and away?
Down.
Down, right? So let's keep it in this down direction. Let me move this oxygen over, and we've got these hydrogens pointed out and away. We've got these double bonds here, right? So we've got to fill in the rest. We've got our methoxy group. Will the methoxy group be sticking up or out and away? Oops, shoot, I gave it away. Will it be sticking up or will it be sticking out and away? Out and away, right? Because if we look at it up here, this methoxy group sticking out away from our diene, it's not sticking inward. So the methoxy group will be sticking out. Our hydrogen will be sticking up. And then we've got our OTMS, right? So if we look at this, this would be the correct endo product for this reaction. Now the cool thing with this reaction is that this TMS group falls off really, really easily. So what I'm going to do is I'm going to draw this using a two-dimensional structure. So we've got our OTMS. We've got our methoxy group that's sticking back. And then we've got this group here, this group here. Our hydrogens are closer to our eye, so I'm going to draw those as wedges. You could draw these bonds as dashes if you want, but it's implied that it's sticking backwards due to that wedge from the hydrogen. Okay, and then I said that this TMS group likes to fall off. And if it falls off, it forms an alcohol. And your product looks more like this. What do you think happens with this product? We've got a special functional group. Think back to the alkyne chapter. Look at you guys started here. It's an enol. What do enols like to do? Tautomerize, right? So what will this product turn into if this enol tautomerizes? Will it be a ketone or aldehyde?
A ketone.
Ketone. So Danishevsky's diene was kind of neat because he showed that it can be used as a clever way of installing ketones. So you've got this hydrogen as a wedge, this one as a wedge, this methoxy group back here. The double bond's now gone away because we've tautomerized it into this ketone. So he was one of the early pioneers of really utilizing Diels Alder chemistry to make very complicated natural products. So it's not uncommon that you go through really complicated chemical syntheses and you see a Diels Alder reaction because it's very stereoselective and you can use it to install a variety of new functional groups in one molecule. It's pretty crazy to think, all right, retrosynthetically, I want to make this molecule. Oh yeah, of course, I would start with these, right? he was very, very clever, and there are a lot of very smart chemists out there that love utilizing Diels-Alder reactions. Make sense? It's a little tricky. That was the most challenging problem I'll throw at you. All right, let's continue on to something more fun. We're going to talk about color for a little bit. This was something we talked about a little bit during our spinach lab when we were talking about UV vis. And what I've got for you guys is a whole bunch of different acenes. So we've got benzene, naphthalene, anthracene, tetracene, and pentacene. If we look at benzene, benzene's a colorless solution, but once we get into tetracene, it actually goes orange, and once we get even into longer and longer wavelengths, it goes more purple. The other thing you can see are some common dyes. We've got indigo dye, a purple dye. The yellow one's super hard to see. That's vitamin A. I apologize, the yellow is not showing up. Then we've got beta carotene. That was the one we saw. Then the one below it, we've got a pink dye. And why do you think going from beta carotene to the one below it that's pink, we went more red shifted? So we went from orange to more of a pinkish color. Maybe because of the oxygens. What else, though? Yeah, more double bonds, right? So that's one thing you may notice is that more conjugation leads to more red-shifted compounds. So you can clearly see with vitamin A to beta carotene to the shrimp dye that we're going more and more red. So we went from yellow to orange to red just by adding in more and more double bonds. I apologize that vitamin A is so hard to see. The main thing too is you can even see with lycopene in tomatoes that if you add even more and more double bonds, you can go all the way deep into the red region. And anytime you see these food dyes, so yellow 5, yellow 3, whatever, they always have this alternating double bond, single bond, single bond alternation. So they're all highly conjugated. It's what gives them that very, very bright color. The interesting thing was there was a group that actually developed a method for predicting the color of compounds. So with the base conjugated dyeing, a simple one, they gave it a lambda max value of 217. And then for every additional double bond, you would add on 30 nanometers. So on the next example, they add on 2 additional conjugated double bonds. And because of that, they added 60 to it. And the observed lambda max is pretty close to the expected value of 277. If you add on alkyl groups, you add another 5 nanometers to your lambda max. So in this one, there's 3 additional alkyl groups. So they added on 15, which hits the estimated value perfectly. And then they came up with methods for endocyclic versus exocyclic double bonds. And so in this top one, if your double bond's conjugated but pointing to the outside of the ring, you only add 5 versus a double bond that's a part of the ring system, that would be plus 39. So I felt like I had to present these. I'm not going to ask you guys to memorize them, obviously, but it's a really useful tool for predicting the lambda max for highly conjugated compounds. You can actually plug in the number of double bonds you have, the number of axial methyl groups you have, whether or not it's part of a ring system, and really closely approximate the color of that compound. I do have one question for you guys. Going back up here. So if we look at this, this goes more red shifted. But then in this region we go from orange to purple, and this goes blue shifted. Does anybody know why? It's a really interesting phenomenon. But if we look at pentacene, pentacene is highly, highly unstable. People have been fascinated with pentacene for a while. But I'm going to draw pentacene a little bit differently. We've got 5 benzene rings that are all fused together. this is another molecular view of pentacene. So if we look at it, pentacene has what's called diradical character. It's actually more stable, having two of its ends basically as naphthalene units. So some of these aromatic compounds do behave a little bit unpredictably. These are under a lot of investigation for molecular electronics, because what happens if we have an infinite sheet of benzene rings that's in a big two-dimensional plane? Does anybody know what that's called? Graphene. So highly conjugated systems have really novel electronic properties, and you may hear about them a lot in the news, especially graphene, carbon nanotubes, buckyballs, things like that. They're very, very popular. But they don't follow the Woodward-Fusor rules that well once they get into long aromatic systems. All right, the last part of Chapter 17 before we do practice problems is something I personally find fascinating. So we kind of take vision for granted, but if we think about our cone and rod receptors in our eyes, they're actually highly conjugated molecules on those receptors, right? And so if we look at the chromophores on our eyes, in the cis conformation, that is without light, they just kind of dock, and this chromophore stays really close to this protein receptor. However, when we hit it with the correct frequency of light, we can actually excite one of those electrons from the HOMO level to the LUMO level, which allows this cis bond to actually rotate, form a trans bond for a momentary period of time. And during this time, this protein can no longer feel that chromophore, and it sends a signal to your brain that you just saw a light of a specific frequency. So conjugation is highly related to vision. We only have a handful of receptors, but I wanted to show you guys something. It's one of my favorite comics. Let's see if I can open it. Does anybody go to the oatmeal? Yeah, it's pretty good. Has anybody seen this on the mantis shrimp? Yeah. Why the mantis shrimp is my new favorite animal. So our eyes contain millions of these cones and rods that enable us to see light through that cis-trans isomerism. Dogs have two different receptive cones, green and blue. That enables them to see some colors, but not all the colors that we see. Humans have three. We can see green, blue, and red. That allows us access to most of the color wheel, right? Butterflies have 5 different color receptors, so they can see deep into the IR frequency and some UV light that we just simply can't see. When it comes to the mantis shrimp, they don't have 2, they don't have 3, they don't have 5 like the butterfly. They have 16 different color receptors, so they can see colors that we can't even imagine seeing. So they can see a thermonuclear bomb of light and beauty. And when you look at them, they're actually really cool to look at. They're very colorful. And then the other thing that blew me away was they fight a lot. And sorry, I'm just going to scroll through this. They're an undersea nightmare because if you actually put them into a tank, they will break through the glass of a tank with 1,500 newtons of force. So they're like this little tiny miracle of nature. I just thought this was really interesting. The other thing, too, is if you guys ever listen to Radiolab, I'm kind of addicted to it. I'm going to go back up. This is somewhat wrong. They have a whole episode where they actually bring up the mantis shrimp, and they said that humans normally have 3 types of color receptors. However, I think it's like a 1 in a million chance that you'll find a female with an additional receptor. So they can actually see deeper into the red region than everybody else. The funny thing is, sometimes they don't know it because, I mean, it's tough to tell if you see a color that somebody else doesn't see, right? Can you really describe that to them? Like, oh yeah, I see this as a different color red. It's a unique trait, but they're actually trying to genetically sequence big paths or big swaths of the population to figure out what groups have these extra receptors, and it kind of becomes this interesting tidbit of human mutation that some people actually have an extra receptor, kind of like an X-Men. Yep.
That's why they think women like pink colors more, because they can see.
Yeah.
Some women can see more shades of.
Yeah, exactly. Yeah, so I'll try to post the Radio Lab podcast as well that talks about vision. It's really interesting, I think. All right, practice problems, since we've got some time. Yep. Shoot. Yep.
Can they see like X-ray vision or something?
No, they just see deeper into the IR region than we typically can see. So they see, so where we would just see all red, they might see different shades of red that our eyes can't make out. Yeah, it's a weird phenomenon. To be perfectly honest, it's beyond me how they ever found out that some people had this mutation, but my guess is they probably had some people in a lab that said, oh, you can't tell this difference in colors, and they're like, no, you can. And so they just genetically scanned people that were able to really finely differentiate colors in the red region and found out that they had an extra receptor. All right, first practice problem. This is actually pulled from, I think, a quiz or exam from last year. Propose a synthesis for the following products through the use of an addition reaction. Clearly indicate the reagents and reaction temperature. So was the reaction run at high temperature or low temperature? So I'll give you guys a minute to work on this one. Does anybody think they've got a solid answer for this? A couple people? I'll give you guys another minute to work on it before we do it as a class. Give you a hint too, this is pretty similar to one of our pods. Raise your hand if you think you got it now. A couple more people. All right, I'll give you guys another minute to work on this, and then we'll try to work through this as a class. All right, let's kind of work backwards through this. Let's take a look at our alkene. Our alkene is tetrasubstituted. Does that mean this is likely a thermodynamic or kinetic product? Yeah, so let's just go through and do the easy stuff. We'll say that this is likely our thermo product, which means we need high temperature or low? High temperature, so I'll just write hot. All right, let's go backwards. And we'll say, all right, in order to make this, we had to have some sort of precursor where there was a carbocation in this location, right? What resonance structure could there be for this carbocation? So we'll go through and say, all right, this has a resonance structure where we have a double bond here and a carbocation here. So now the question becomes, all right, if we have HCl, what would our precursor be for this intermediate? Yeah, a double bond, right? So we can go through and we can say, all right, if we draw this, we would have a double bond right here. And then I'm going to fill in our gaps for the mechanism, right? So we've got HCl. This double bond will attack this proton, kick off our chlorine. We get this highly resonant stabilized carbocation. And then this chloride can add into this carbocation center and give us our thermodynamic product. So just work through these backwards. Don't overwhelm yourself and make things too hard. It's easy just to go stepwise backwards and go from there. Oftentimes there's not one right answer for these two. So as long as your answer makes sense, that's all I care about.
What about using the Alder reaction?
What's that?
Alder reaction.
Diels Alder?
Yeah.
In this case, I said addition reaction, so not Diels Alder.
Okay.
Yeah. Let's do a Diels Alder one though, because we've got like 4 more minutes. Here's another practice one too. I'll leave that in the course notebook if you want to practice it. But let's do this one. This one's from another exam. Chloridane, an insecticide, was banned in 1988 due to its adverse environmental and health effects. Identify which reagents you would need to make chloridane via Diels-Alder reaction. It looks scary, but it's not too bad. It looks a lot like our previous Diels-Alder reactions. So the first thing I do when I look at a Diels-Alder product is I try to identify where my new sigma bonds formed. So let's try to identify our sigma bonds. Was this a new sigma bond, do you think? No, that's too far away from the double bond on the opposite side, so that's not a likely candidate. What about this sigma bond? No. Again, that probably isn't a good candidate as well. What about this one?
Yes.
Okay. And what about this one?
Yes.
Okay, so let's work backwards and fill in these reagents. That means we had to have some sort of 5-membered ring, right? That red portion. So let's fill that in on the left. This had to be some sort of diene. We had a chlorine coming off here, chlorine coming off here, a chlorine off one of these carbons, so that would be this chlorine over here. And then this bridgehead carbon right there had 2 chlorines coming off of it, so I'll pop on 2 chlorines right here and right here. That means we have to account for our other substituent, which is this 4-membered ring. And this 4-membered ring must have had a double bond since it's a dienophile. And we go 1 carbon over. We must have had some sort of chlorine here. And we must have had some sort of chlorine here. Does that make sense? So first thing, easiest thing to do is identify your new sigma bonds and then break it apart into 2 separate fragments. Your diene is the one that has the double bond in the product, and your dienophile is the other fragment. Do you guys want to do the mechanism? Yep.
Are the double bonds always that position?
For the red product or red starting material?
And blue, yeah.
Yes. In this case, those are your only options. All right, let's not do the full mechanism because we're running out of time. The other thing you might notice with chlordane, so you see how this ring's pointed down? This again is your endo product. That means that our hydrogens that are not drawn are sticking out. They're in the exo position and that blue ring's pointed down endo. So just remember the endo product is always preferred. All right, good luck studying. Tomorrow my office hours will be 10 to 11 because I have a meeting later in the day. So 10 to 11 in the fishbowl if you guys want to do sapling or have any questions. Quiz on Monday, yeah.